So far we've been defining simple rates of return that are just based on the percentage change in price. One of the features of these simple returns is that when we look at the relationship between multi-period returns and single-period returns, it was multiplicative. So the 1-year return was a geometric average of 1-month returns, for example. And I made the comment that this multiplicative relationship is annoying from the point of view of modeling. And it's better if things are additive. So it turns out that we can define a rate of return that gives us an additive relationship between one-period returns and multi-period returns. And this rate of return that gives us this property is called a continuously compounded return. Now, the definition of a continuously compounded return, I'll use little RT here to distinguish the continuously compounded return and big RT to represent the simple return. The continuously compounded return is just the natural logarithm of 1 plus the simple return. Because 1 plus the simple return is the ratio of prices, the continuously compounded return is also the logarithm of the ratio of prices. This is a definition. Okay? Now, because the continuously compounded return is defined from the simple rate of return, we can go backwards and forwards between these two. The logarithm of 1 plus the simple return is the continuous compounded return. So given a simple return, we can solve for the continuously compounded return. Right? Similarly, if we know the continuously compounded return, we can reverse this relationship. We can exponentiate the left-hand side and the right-hand side and get that the simple return is e to the continuously compounded return minus 1. So given the continuously compounded return, we can use this relationship and solve backwards for the simple return. Okay? Now, because of the logarithmic transformation here, the continuously compounded return is always a smaller number than the simple return. Okay? And now, just a digression a bit on logarithms and exponentials. So just hopefully everyone knows these relationships. The logarithmic function looks like this. So if this is x, and I'm computing the logarithm of x, the logarithmic function looks like this. So the log of 0 is minus infinity. The logarithm of 1 is 0. The exponential function is the inverse of the logarithmic function, all right? Which means when you take the logarithm of the exponential of x, you get back x. And if you take e to the logarithm of x, you get back x. The exponential function looks like this. And so this would be e to the x. And e to the 0 here, e to the 0 is 1. All right, so the derivative of the logarithm, the first derivative of the logarithm of x is 1 over x. The derivative of e to the x is e to the x. Logarithm of x times y is the logarithm of x plus the logarithm of y. The logarithm of the ratio is the difference in the logarithms. And then we have the logarithm of x to the power y. That's y times the logarithm of x. E to the x times e to the y is e to the x plus y. E to the x times e to the minus y is e to the x minus y. E to the x raised to the power y is e to the x times y. So when we work with continuously compounded returns, we work with these properties of logarithms and exponentials, and it makes our life a little bit easier in terms of computation. So what is the interpretation of a continuously compounded return? Well, the continuously compounded return is just the continuously compounded growth rate of prices between two periods. So if we look at e to the RT, so this is the exponential growth rate of prices between time t minus 1 and t. That's e to the logarithm of 1 plus the simple rate of return. That's e to the logarithm of pt divided by pt minus 1. Now, e to the logarithm, these are inverse functions, so that gives us pt divided by pt minus 1. So e to the RT is the ratio of prices. Now, we can multiply both sides by pt minus 1, so we can get e to the RT is like saying pt minus 1 times e to the rt is equal to pt. So that the price at time t is the continuously compounded growth rate in prices between t minus 1 and t, where the continuously compounded growth rate is little rt. Okay, so that's the interpretation of little rt. It's just continuously compounded growth. Now, a property of continuously compounded growth rates is the following. So we know that the continuously compounded growth rate is the logarithm of 1 plus the simple rate of return. If the simple rate of return is small, that is, if it's close to 0, so again, if we're thinking of monthly rates of return, you know, that might be 1% or 0.5%. That's a number that's pretty close to 0. So it turns out that the logarithm of 1 plus the simple rate of return is approximately equal to the simple rate of return when the simple rate of return is close to 0. And this result can be justified by using a very useful mathematical result known as first order Taylor series approximation. So if you remember from calculus, Taylor series approximation says if I have a function f of x and I want to approximate this function at some point, say x equal to x0, the Taylor series approximation says f of x is equal to f at x0 plus the derivative of the function times x minus x0 plus some remainder term. Okay? Now, if we take our function f of x to be the logarithm of 1 plus x, and we take the point that we want to evaluate the function at x0 equal to 0, then let's just plug back into this relationship. The derivative of f of x, the derivative of logarithm of 1 plus x, is 1 over 1 plus x. That comes from the properties of the logarithmic function. And if we evaluate this derivative at x0 equal to 0, then the derivative of logarithm of 1 plus x0 is 1 over 1 plus 0. That's just 1. So then when we look at the Taylor series approximation using this formula, when we use f of x as the logarithm of 1 plus x, we get the logarithm of 1 plus x is approximately equal to f of x0, which is the logarithm of 1 plus 0. That's the logarithm of 1. The logarithm of 1 is 0. And then we have the derivative of f of x, which is 1, times x minus x0. x0 is 0, so we have x minus 0, which is x, so we get 1 times x. So from the Taylor series approximation, the logarithm of 1 plus x is equal to x plus some remainder term that's small. Now this is, again, we use this approximation a lot. And again, the underlying background is the use of a first order Taylor series approximation. Now from the point of view of computation, a continuously compounded return can also be computed as the logarithm of the ratio of prices. Now again, from the properties of logarithms, the logarithm of the ratio is the difference in the component. So the logarithm of pt divided by pt minus 1 is the log of pt minus the logarithm of pt minus 1. And so we'll use little pt to represent the logarithm of the actual price. So we can also compute continuously compounded returns by taking the difference in the log prices. And this is common in economics, right? So very often when you see macro data like real GDP, you plot it over time, you often see the plot of the logarithm. And so why do you plot the logarithm instead of the price? So what's the interpretation of the slope when you plot logarithms? The growth rate between one period and the next. So the elasticity in this case would be the same as the continuously compounded growth rate between two time points. So when you plot log GDP over time and you look at the slope of that graph, you essentially get the growth rate between two time periods where the growth rate is the continuously compounded growth rate. The same thing with prices. If you do a plot of log prices, then the slope of the log price graph represents the continuously compounded return between two time periods. All right, so let's do some examples here. So let's compute continuously compounded returns, for example, from Microsoft. So again, PT minus 1 is 85, PT is 90. Our simple rate of return is 5.88%. What's the continuously compounded return? The logarithm of 1 plus the simple return. so it's 5.71%. So the continuously compounded return is slightly smaller than the simple return. So what's the intuition of why the continuously compounded return is smaller than the simple return? So again, remember, the simple return, you're compounding once over the period. The continuously compounded return, you have continuous compounding over the period, right? So with continuous compounding, the rate of return can be smaller and you're getting the interest on the interest and so on. So it's the fact that we're compounding interest continuously when we use the continuously compounded return means that this return is smaller than the simple return. So this is compounding once. This is compounding continuously over the period of time. So you get that result that RT is slightly smaller than big RT. Continuing on with continuously compounded returns, one of the nice features of the continuously compounded return is the relationship between single period continuously compounded returns and multi-period continuously compounded returns. So here we're going to look at a 2-period continuously compounded return. So again, I use this notation, little RT parentheses 2, so this is the 2-month continuously compounded return. It's, by definition, equal to the logarithm of 1 plus the 2-period simple rate of return. Now, 1 plus the 2-month rate of return is just the ratio of the price at time t divided by the price at time t minus 2. So we can get that the 2-period continuously compounded rate of return is the difference in the log prices between time t and time t minus 2. And we can also get the interpretation, this 2-month continuously compounded return is the continuously compounded growth rate of prices between t minus 2 and t. Again, so that's again, we're just defining the 2-month continuously compounded return. So now we want to ask the question, what's the relationship between the 2-month continuously compounded returns and the 2 1-month continuously compounded returns? So we make use of the fact that the 2-month continuously compounded return is the logarithm of pt divided by pt minus 2. But we can do this trick. We can multiply and divide by pt minus 1. So we get that the 2-month continuously compounded return is the logarithm of the product of these two. Now the logarithm of the product is the sum of the logarithms. So the 2-month continuously compounded return is the logarithm of pt divided by pt minus 1 plus the logarithm of pt minus 1 divided by pt minus 2. But this is just the continuously compounded return between t minus 1 and t. And this is the continuously compounded return between t minus 1 and t minus 2, or t minus 2 and t minus 1. So we get that the 2-month continuously compounded return is the sum of 2 1-month continuously compounded returns. Notice that it's nice and additive. When we had simple returns, the relationship was a geometric average. It was multiplicative. So this is the great advantage of continuously compounded returns for doing analysis. When we do probability modeling, we find that this additive nature will greatly simplify a lot of models. Say, for example, if continuously compounded returns each period are normally distributed, then the 2-period continuously compounded return is the sum of 2 normal random variables. The sum of 2 normal random variables is another normal random variable. Normality is closed under addition. It's not closed under multiplication. And so we'll find that the use of continuously compounded returns helps us tremendously in doing modeling of asset returns. Okay, so just going with an example, we have a 2-month return on Microsoft. PT minus 2 is 80, PT minus 1 is 85, PT is 90. And then the 2-month continuously compounded return is the difference in the log prices. So that's 11.78%. Now the 2 1-month continuously compounded returns, RT is the difference between log 90 and log 85, so that's 5.71. RT minus 1 is log 85 minus log 80 at 6.07. And so the 2-month return, the sum of the 2 1-month returns is the same thing here. Now, notice that the 2-month continuously compounded return, 11.78%, is smaller than the 2-month simple return. Okay? And again, this is because we have continuously compounded interest over 2 months, and this is just simple interest over 2 months. So in general, if we have a K-month continuously compounded return, so let's say we have a 12-month continuously compounded return, that's the logarithm of 1 plus the 12-month simple return, and that's just the logarithm of the ratio of the price at time t and the price at time t 12 months prior. And using the same trick, we can show that the K period continuously compounded return is the sum of K single period continuously compounded return. So we have this additive relationship over time. So again, this makes our life easier from a modeling perspective.